Narnia. This series mainly covers things like buffer overflow, binary exploitation, and so on. Okay, so let's get started. This is the server we need to connect to, and this is the port. Okay, and this is the username and password. So once we have this information, we can just log in, and you can see that data for these levels can be found in Narnia. Okay, so /Narnia. So let's go. SSH Narnia 0 at narnialabs.org -p. So this is the username, and Narnia 0 is also the password. Now we're here. Let's move to /Narnia. Okay, so here we can see a bunch of files, right? So for Narnia 0, you can see that there is Narnia 0 and Narnia 0.c. So if you just see the permissions, you don't have permissions to open other files. Okay, as Narnia 0, you can only open these two files. Okay, so this will be our point of interest. You can also see that this particular file is owned by Narnia 1. Since it has setuid permissions, Narnia 0 can also execute this file. Let's clear that. Let's open Narnia 0 and let's see what it has. Okay, correct val's value from 0x41414141 to 0x dead beef. What they're trying to say is there is a variable called val, so you need to correct this val's value. Okay, so we don't know how to do that, right? We don't know the code, so we just typed some random value and then we'll see the output. If you see ASCII table, this 41414141 is nothing but A. Okay, so hex value of A. Let me show you that. ASCII table.com. You can see that 0x41 is nothing but capital A. We know that this is A. Okay, so we need to change this part to this. Let me type some characters to show you what it actually does. Okay, let me type bunch of B's. Let's see what happens. As you can see, it has changed it from 41 to 42, which means this capital B refers to 42, right? So what we have essentially done is we have changed this val's value from 41414141 to 42424242. We don't know how much length this is, right? But they have given a file called narnia.c. Let's see that file, 0.c. So this is the file you got. So these are the standard headers, standard C headers /include something something. This is the main code. So here they have said this is long integer which has the value of this, and then they have said that this is some kind of character and this name of it, and it contains 20 characters. And we have also seen these two values right on the screen right here. Okay, so basically they are just simple printf, and then we need to enter some value here. So scanf is asking for 24 bytes of data. So S is refers to string, so 24 bytes of data. Once we have inputted the data, then it shows the buff value and the val's value, and then it is going to check this val's value to dead beef. Then it is going to take the user permissions. It's going to get this UID and then set this UID. And then what is it going to set to? It's going to set to this shell. Okay. Once this shell is there, then it is going to end right here. So this else statement will not execute. And then it's going to return 0 and then it's going to exit. If it is not equals to dead beef, then it's going to print way off and then exit with exit code 1. How to imagine this part? So you need to understand at memory level what's going on. Okay, so whenever we start assigning some values to variables or some functions, all these things come in the stack format. Okay, so to imagine that, these two images would help. So this is how the program usually runs. Okay, it remembers the arguments. If we have any arguments, this one we don't have any arguments. It's going to keep adding all the important things, and then once we start executing the program, we know that once we reach to the val's value, we are actually setting it to 0x41414141. Okay, so we already know that, right? But what about this one? We are giving a space of 20 characters so that later you can enter something into it, right? Since we give the buffer of 20 characters, we can enter 20 characters or 20 bytes of data into this array. Okay, so this is how it actually stores the memory. It starts from highest memory and then keep allocating data as it starts adding arguments or variables or functions in this stack format. Okay, so this is the memory stack which actually happens. So in this image you can actually understand what's really going on. So we know that long val is actually given as long integer. It can accommodate 8 bytes, but we have only given 4 bytes of data into this, but it can still allocate 8 bytes of data. So what about this one? We have given 20 bytes of data to this buff variable so that it can allocate 20 bytes of data. You can count. So 1 2 3 4, 1 2 3 4 5, 5 4 is 20. So when we are accepting data into the buff variable, we are not accepting 20 bytes only, we are accepting 24 bytes of data. So it can start allocating data from the top, and once it reaches 20 bytes, it can still allocate 4 more bytes. And where does this bytes go? This 4 bytes of data will go into the next long val variable. So we'll see that in action. So now I will show you how to understand what's happening at memory level. Okay, so for that we can use GDB. So it is a debugger of a binary code. So we'll just say that Narnia 0 to be opened with the debugger. So it is going to ask you enable debug. Okay, so just accept it, and then now you are in debug mode. Okay, so you want this binary program to be converted into assembly language so that you can understand the code. For that you can say that disassemble main. Okay, so as you can see, this is a dump of assembler code for the function main. Okay, so the program starts from main function, right? So everybody knows this. So these are the values from which the memory distance of this particular instruction from main. Okay, so when you want to analyze this particular value, you say main plus 7. So our point of interest is at the scanf because we are entering this data. So this is user controllable data, right? We'll assign some breakpoint at this area. Okay, so how do we assign it? We'll say break and asterisk. So this is the pointer you're trying to say. So where is it? It is at main plus 54. So if you see this value, so this value should be equal to this value. Okay, so 91FC, you can see that 91FC is here. So basically we have assigned a breakpoint right here. So what does breakpoint do? So breakpoint just halts the program at this particular location. So let's enter some values. So to enter these values, so you have to run the program, right? So you say run, or you can simply add R, so which also says that it can run. Okay, so initially I'll just run this. Here's your chance. So we need to enter some data. Let's enter some data and see what happens. And as you can see, it is just halted at this breakpoint. Okay, so what is this breakpoint? So this is a stack pointer. So you can say that show 20 words of memory from stack pointer. So to understand this thing, I'll just tell you what it is. So X is to examine. Okay, so you need to examine some data in the memory. Okay, so how much memory you want to examine? You want to examine 20 words of memory. Okay, so we'll see the words of memory. What does words of memory actually mean? Okay, and then this X says that it should be shown in hex format. If you hit enter, you can see that this is the data that is being dumped. So here you can see that 1 2 3 4 and 1 2 3 4 5. So 20 words of data. Okay, 5 4 is 20. So 20 words of data from the stack pointer. So we know that we have entered some data, right? That data is BBBB, right? So we need to see this BBBB in memory. So what is this capital B refers to in ASCII table? It is 42, right? So you can see that is 0x42, 42, 42, 42 right here. And then you can see some null data, which is an empty memory that is allocated to this buffer variable. So how much is it? So if this is 4 bytes, 1 2 3 4, which is this one. So 1 2 3 4 and 5. So 5 4 20 again. So 20 bytes of data is allocated to the buffer value. We know that val's value is 41414141, right? So what happens if I keep ABCD instead of this value? Okay, let's see that again. Okay, we'll just say run, and then we need to say yes because it will start from the beginning. So this is my chance, so I'll just say ABCD. Okay, so and again I can say the same thing. So here you can see that this ABCD is given in reverse order. Okay, 41 42 43 44, which means it is following little endian format. Okay, so if you can just check little endian, so this is the format it is actually following. Okay, so big endian format will go from left to right, but little endian format will go from right to left. To do that, we can say we have to give DCBA, and then you can actually see that it will come in straight order. Okay, so 41 42 43 44. So conclusion, so if you want to write something in memory, we should write in reverse order. Okay, so now question, so can we write the same thing directly to the memory? Let's try that. Let's try to write the hex values right now. Okay, so to enter hex values you have to say \x, which means you are saying that you want to input hex values. Okay, so here you can say 42 and then just copy it just 4 times, Control C, Control V. So now you have given 4 bytes of hex values. So let's see what happens. So as you can see, it was not possible. So each character is detected as a byte. Okay, so you cannot input hex values directly like this. So what you have to do is you have to pre-process this hex value and then send it directly to the memory. So you cannot do it right here. So for pre-processing you have to use pipe symbol so that you do the pre-processing first and then directly send it to the memory. Okay, we'll see how we can do that. So next you can see that since each character is detected as a byte, so we can see that there is 16 bytes of data that is being filled over here. Since the scanf can take 24 bytes of data, so can we override this value with 42424242, which means B. So let's see that. So let's see if we can do and override this value. Okay, so let's say run and then run from the beginning, and let's say B, and just copy this and just type 5 times, 1 2 3 4 5. Okay, so 5 is nothing but 20, so you have to say one more. Let's see. So as you can see, you were able to override this value. Once you have overwritten this value, you can just continue the program. Okay, you can say continue, or you can just type C for continue. Okay, here you can see that val's value is been overwritten. Let's go back to the original program and exit this debugger, so we know how to do that, how to override this. So all we can do is do some pre-processing and convert these hex values and send them directly to the memory. Okay, so to do that you can say echo -e, so which will actually pre-process it, or you can give some shell function which is printf, and you can still do the same thing. Okay, so let's try with printf. Here what you need to do is you need to enter some data. So you already have this B, right? 1 2 3 4 5, and then just type it. Okay, let's see, Narnia, and let's see what happens. Okay, this output is sent as input to the scanf right here. Okay, so it has detected something like this. So let's add 4 more B's, and you can see that it is completely overwritten. So we'll just remove the last 4 characters, and here since this printf is a part of a shell function, so you can say that I can pre-process right here. Okay, by giving hex characters. So we know what characters to be given, right? Here let's try to give the same thing. Okay, So pre-process this one and say 4 bytes of B. Okay, let's see what happens. So we were able to pre-process this value and send it directly to the val's value. Okay, so we'll just remove this because we need dead beef. So we'll just remove this value and say that, so we need to give dead beef in reverse order. You remember, right? Little endian, DEAD, BE and EF. Okay, it will pre-process the whole thing and then send it to the scanf of Narnia 0. Okay, as you can see, we were successfully able to change it to dead beef, but we did not get the shell. Okay, so let's see why that is right here. So this function is able to get effective user ID and it is also executing shell, but it is just simply closing with return 0. Okay, it's not stopping right here. So we need to keep that input stream open. Okay, so there is a small trick you can use to not close the input stream. You can keep this whole thing in the brackets. Okay, to keep the input stream open, you need to end this command, and you can also keep cat, because cat can keep the input stream open. Okay, so I'm just going to copy this and just going to show you how cat can keep that input stream open. So if you simply type cat, so you can see that it is just blinking right here, right? So it's just waiting for us to input something. So the input stream is open in this case, right? So if we enter some data, it will give that as an input to the cat command. And this cat command, where is this cat command going? So it will go to the shell. So this particular command will say that, so this is a printf, and this will give this much data and pre-process it and send it as an input to the Narnia, but also keep the input stream open. Let's see what happens. As you can see, it is blinking right here. So this dead beef has opened a shell right here, and this cat command is keeping that input stream open. So which means we have essentially have this shell open right now with the effective user ID of Narnia 1. So to confirm that, I can say who am I, which is Narnia 1. Okay, actually currently you have a shell, but you can get the password anyway. But what I want to show you is, do you have to keep all B's? No, you don't have to keep all B's. You can essentially remove all this and keep some random characters of 20 bytes and followed by this dead beef, and still it would work. So who am I? Narnia 1. So understand this underlying logic, because this would help you solve this really easily. Okay, so now you know that the password is /etc/Narnia _ pass and Narnia 1. So this should give us the password. Okay, so I hope you have understood this. And there is one more thing I want to tell you. Okay, so is the code secure? The code which is given right here, is this code secure? Is this the correct way of writing the code, right? So turns out that this code, the way that it is written is secure, but deliberately they have made this into 24 bytes. Okay, check this out. So when using scanf to read strings, it is important to limit the string length to prevent the buffer overflow. Okay, so this particular code can actually prevent buffer overflow, this particular string, because we have limited it to 24 bytes. Okay, so let me tell you one more thing. So let's use the GDB to execute Narnia 0 and disassemble main breakpoint at main plus 54. So we know that this is the particular location, right? So now let's run it. So let's give lots of B's this time. Okay, so this is definitely more than 24 bytes. Will it even bypass this 24 bytes and go beyond 24 bytes? We know that it goes till 24 bytes, but does it go beyond 24 bytes? Let's check this out. Stack pointer. So here you can see that it can go till here only. It will never go beyond 24 bytes of data. So from this, you can say that, so the way it is written is secure, but they deliberately changed this buffer to 24 bytes so that you can get something out of here. If it was 20 bytes instead of 24 bytes, it would never overflow this buffer and reach this buffer. Okay, it will never do that. Okay, so we've already done Narnia 0 and we got this for Narnia 1. So SSH Narnia 1 and paste the password, and here we got a shell. So let's go to cd Narnia and ls, and we have already done this thing. Now we have to do this. Okay, so same conditions, Narnia 1 can execute it, but when Narnia 1 executes, it can execute as Narnia 2. So we can try to get something out of this as Narnia 2. Okay, so we also have a C file, so let's check that file. So this is what we got. The main function has a pointer function which doesn't take any arguments and returns an integer. Okay, so that's what it means. Next, they have given get environment this, which means egg has to be one of the environment variables. So if this is set to null, then print this and exit. Okay, or else print trying to execute egg. It is going to get the value of this environment variable and it stores it in this variable, then it executes it. Okay, so if we have a shell in this variable, then this variable is going to execute a shell and pop up a shell for us. Okay, let's do some testing. Narnia 1. Okay, so it detects that egg variable doesn't have anything, so it just gives this. So what we can do is we can try to see what's inside egg. So since it is saying that it has nothing, so it should have nothing. Okay, so as you can see, it returned nothing. So let's say export egg equals to something. Okay, let's say a. So now this value is going to store in this variable. So now echo $egg and we have this thing. Let's see what Narnia 1 replies this time. Okay, so it says trying to execute egg, segmentation fault. Okay, there's something that's not accepting it. So let's see what is happening inside. Okay, so gdb Narnia 1 and yes, and here we have it. Okay, so disassemble main. Okay, so here we are getting the environment variable. So let's try to see this call. Okay, so this is where we are calling that function. So let's see what it has. Okay, so break at main plus 75. Okay, simple enough. Okay, so now we have set a breakpoint right here. Okay, so now let's run it and let's see what happens. Okay, so it says trying to execute egg. Let's examine 25 words of memory at EAX register. Okay, so this is the same register that we have selected here. Okay, so let's see what we have here. You can see that 41414141 exists, which means this variable is being replied to us. Okay, so it doesn't have any kind of shell code or anything like that, so it just trying to execute it and then it stopped. So if we just continue this with C, it will just say segmentation fault. Okay, because it doesn't know how to execute this. So if you replace this with a shell code, once it executes, we will pop up a shell. Okay, so let's see how it is done. And even when you're popping up a shell, you need to take care of these permissions. Okay, you always need to remember when you start a new bash shell, it will reset effective user ID and effective group ID to the real user ID and real group ID, which means it is reset to Narnia 1. So it will not be a Narnia 2. Let me show you what I mean. Let's go to shell storm. This is where we can get all types of shell codes. Okay, so one of these shell codes is something like this. Okay, so if you go to 585 in this list, you can get something from Magnifico. Okay, so this is a shell code. Okay, so you can use this to pop up a shell, but you cannot get the Narnia 2 permissions with this shell. Okay, it simply executes this. Okay, so let me show you what I mean. So you can say egg equals to printf this and then exit with this, and now this is pre-processed and the shell code will be stored in this egg variable. Okay, and you can execute Narnia 1 from here itself. Okay, so let's see what happens. So here you got a shell, right? But if you type who am I, you can still see that you're Narnia 1, you're not Narnia 2. Okay, the effective permissions is not given to this. So to preserve that effective permissions, you need something else. Okay, so let's exit out of here. So let's get some other kind of shell. So if you go to 607, you can get something like this. Okay, so this particular shell will execute something like this. Okay, bash -p. Okay, this is something like bash -p. So what this -p would actually do is it will preserve the privileges of an effective user. Okay, it will not replace it with the real user. So let's copy this, and to work with this code really fast, all you can do is keep a dot at the end. Okay, so what this dot will do is it will use this dot as concatenation in Perl. Okay, Perl -e and print. What this will actually do is this would actually convert all of this into a single string. Okay, so this will just concatenate all this other strings and make it into a single string. And since you are executing in a bash shell, so you have to keep this backticks so that this Perl will execute and then store it in egg variable. Okay, so let's do the same thing. Control Shift V and then space and say Narnia 1. So let's see what happens. Here it executed this shell and we got a new type of shell right now. Okay, not this kind of shell. This is a new shell. This is a bash shell right now. Okay, so let me see who am I. And as you can see, we are Narnia 2. Okay, so this particular shell contains this -p. Okay, so that's why it preserves this effective user ID and effective group ID. So that's how it works. Okay, so let's clear this. Okay, cannot clear this, but anyway, so cat/etc/Narnia_pass Narnia 2. Okay, so now we got this and let's store it right here. Right, so can we solve this in any other way? So other than using Perl, so you can use echo, but you have to remove all these quotations and dots and make this into a single string. Okay, and then if you just try to execute Narnia 1, it would still pop up same shell. Okay, is there any other way to solve this? Okay, so you can solve this in one more way by using printf. Okay, so you do the printf and do the same thing just like you did with echo command, and then you can still try to execute Narnia 1 and it would pop up this shell. You need to understand that this is just like a bash script. Okay, so you give some variable and then you execute the program. You need to also remember that this egg variable is not exported. Okay, so you did not do export and then you did not do this. Okay, so you just run it like this. So what do you think is stored inside this egg if export is not used? Okay, so let me see echo egg. So as you can see, even though you stored the shell code, it is not, since it is not exported, it still contains the old value of the egg variable. Okay, so keep in mind, if you don't want to export, you can directly execute it like this. But if we want to export, all you have to do is you have to select everything and do this first, so that it will be stored in this egg variable. And then if you try to execute Narnia 1, this would pop up a shell. Okay, all right, let's do this. Narnia 2, there is this cherry tree and this one. All right, let's begin. We know that the files exist in /Narnia, so let's see this. We know that we have already solved these things, so we don't need that, but this one. So these are the two files that we need to care about right now. Okay, Narnia 2 binary and Narnia 2.c. Okay, so before jumping in, let's see what this Narnia 2.c has. Okay, so this is the main function, and it accepts some argument, and it has a buffer that is set to 128 characters. Okay, if argc equals to 1, which means if no argument exists, then it's gonna print this usage and then exit. But if some argument exists, then it's gonna just take that argument, put it inside this buff, which is this one, and then it is going to print that buff. Okay, and then it's going to return 0. So where do you think is the problem in this code? Okay, so this is the line that is problematic, because there is no limit of how much buffer it can take. Okay, but here there is limit, but it doesn't matter. This is the one that is vulnerable. Okay, so let's try and execute Narnia 2. Okay, it expects an argument. Let's give an argument, and then that is being returned over here. Let's see if we can give a bigger argument, because we know that it expects at least 128. Okay, so we need to give more than this. Okay, let's copy that, and let's say there is a shell in which I'm going to execute Python. So there is no Python actually. Okay, so let me show you what I mean. Python. Okay, there's no Python, so we have to say Python 3. Okay, so Python 3 exists, so we need to give a Python 3 syntax. Okay, so you say Narnia. Okay, so let's do the Python 3 syntax, and then we'll see Narnia. Okay, so Python 3 and then -c print, you can say 128 times capital A. Okay, and then end it with this. Okay, so now you can see that you can execute this code, right? We use that same thing with Narnia. Okay, so let's say Narnia 2 and then this, but this needs to be enclosed in a subshell. Okay, so let's see what happens. Okay, so it is able to give us our data back. So let's go back and change it. Let's change it to 4 and let's execute. You can see that it is segmentation fault, which means this data is too much for it to handle. Okay, so let's give a little bit less data. Let's say 135, still segmentation fault. Let's say 130. Okay, it's able to give 130. Okay, so we're getting close. 132 and segmentation fault. So we're getting really close. Now let's say 131. Okay, so 131 is okay, but 132 is causing an error. So let's see what happens at the memory level. Okay, so let's see Narnia 2, and before that you can just say that open quietly. Okay, let's copy this Python script and let's hit enter and let's say yes. Once we are in GDB, let's say disassemble main, and then it just disassembles the whole main. So we know that initial printf is not necessary because it's just checking if any arguments are there or not, but this one is actually copying it and then printing it back. Okay, so let's give it somewhere around here. Okay, so let's hold it here, and then we'll examine everything else. Okay, so let's say break at main plus 81. So that's what it means, right? Main plus 81. So this is where we want a breakpoint. As you can see, this address and this address are same. We have established a breakpoint right here, and then we want to run this an argument something like this. Okay, so let's see what happens. So it executed and it stopped at the breakpoint 1. Let's see if it exits normally or not. Okay, but we know that it exits normally, so let's continue by pressing C, and it exited normally. Okay, let me do the same thing again, but this time let's give 32. Okay, 132. Let's continue, and you can see that it's causing a segmentation fault. So let's keep doing this, and let's see what happens if we just increase some more data. Okay, so let's continue. Okay, so this time we're getting a new error over here. Okay, so we did not get this previously. Okay, so as you can see, we didn't get that previously, but this time we actually got a different kind of error. So this is basically return address, something like if something goes wrong, go to this address. In this case, let's try to examine some stack pointer with 50 words of memory from stack pointer. Okay, so let's do that in reverse. Okay, you can say reverse means if you said from down up, not from up down. So let's see what happens. So your A is actually starting from here and ending right here. Okay, the return address has 0x414141 somewhere, we don't know. Okay, so let's do one thing, and let's change this to, let's say, some bytes. Let's say 131 plus 4 times B. Okay, so let's say B, 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 B. We have to find out where it actually returns this address. Okay, so let's say yes, and then continue, and as you can see, one more byte needs to be pushed. Okay, so here let's keep 132A, and now let's run it and continue. As you can see, we have replaced the return address with 42424242. Okay, if we make this return address pointing to a shell code, then we probably can get a shell, right? So let's find a shell. So we have used this shell previously, but this is of no use, but we'll just tell you why we can use this. So replace this with shell code, and say print some bytes, and then after that bytes, let's give a return address. So we don't know the exact return address, right? So let's try to find that return address. Okay, so let's give 50. I think 50 should be enough. Okay, so the code starts from this area. Okay, so let's give this memory code in here, plus double quotes again, \x this, and then \x this, and then \xff \f. Okay, so this is the return address. This is where it has to return to. Okay, and in between, okay, so this is the shell code we're executing, right? And then we have to add some data here. Okay, so this data has to be such that if you add all of these bytes and this bytes and the data which you're going to input, so it should be added to 136, because that's what we have inputted here, right? 132 plus 4, 136. Okay, so you need to make this whole thing into 136 bytes. Okay, so we already know that this shell code is 23 bytes. Okay, so what you can do is you can say 132 minus 23 and multiply it by some random character, let's say A. Okay, and then add this at the end. Okay, so this will be your shell code. Let's see if this one works. If this doesn't work, then we have to follow some other way. Let's see, run, enter, and then let's continue. So as you can see, it is just pointing to 4 on 4 on 4 on 4 1. Okay, which is not what we expected. This particular return address that we have given is again pointing to a different address. Okay, so we don't want this to be executed as a part of this. Okay, so what we want is for this shell code to execute. Okay, so we don't know exactly where that is, so we need to say examine 50 words of memory and then at stack pointer. So here you can see 50 words of memory from stack pointer starting from here. Okay, so here you can say 4 on 4 on 4 on 4 1, and then above this there should be more data. Okay, so let's give 250. Okay, let's see all the data that is there. So it's again starting from here. Okay, it's saying that this is the thing, and from here there are lots of other data, and let's keep going, and as you can see we have more of 4 on 4 on 4 on 4 1 data here. Okay, so where did this come from, right? Let's do one thing. Let's give something like a NOP sled. So if you see this code, we have given shell code in the beginning and then some random characters. Then we are giving a location in memory, so where it is going to go and check for certain code. Okay, so we're going to slightly change this, and let's say we're going to give the same shell, but this one has to be in the beginning. Okay, so and say plus, but this one has to be NOP sled. Okay, so whenever the program detects hex code 90, it is simply going to ignore that hex code. Okay, so by ignoring, we are saying that it is no operation hex code, so that is called NOP. Okay, so when we give these many NOP characters, we are basically going to say somewhere in middle of these hex code 90, which is NOP, if you reference it, it is going to just come down to the shell code, and then this shell code will actually execute. Okay, so let's try this and let's see what happens. Okay, so here we also need to take care of the location in memory, but currently we're just gonna paste it and let's see what happens. Okay, so when you execute that, so you hit a breakpoint and let's continue, and here you got a different hex code. Okay, so looks like you cannot use Python in this case. So let's see the stack pointer. So there are lots of these things, but it wouldn't matter. Okay, look at this. So we're getting lots of these characters, but it is not hex 90. So we need to have a different kind of payload over here. Okay, so instead of using Python, let's use something like echo or printf or something like that. Okay, so to do that, you have to type all the characters. Okay, so something like this. So you have to type 136 characters, which includes this no operation characters, and then the shell code, and then this reference where we are referring to. Okay, so we know that the reference is D248, and let's see what happens. Let's begin from the beginning. Let's continue. Okay, so we have a different reference point this time. Okay, so let's see what happened in the stack pointer. Okay, so here let's continue. Okay, look at this. Here we got all this NOP sled, right? So let's pick somewhere in between so that it will just come down and execute this shell code. Okay, so something like this. So let's give some reference. Let's say 54. Okay, D554. Okay, so just go back to the payload and keep that it is D5 and 54. So D5 and 54. Okay, cool. We are saying whenever this code finishes, let's go to this location, and then this location is this location, and then it is going to just slide down to the shell code, and the shell code will execute and it will pop up a shell. Okay, so let's see if we are correct. Okay, so let's continue, and look what we got a shell, right? So let's use the same payload outside GDB. Okay, so let's exit out of here and exit out of here as well. Okay, so you're gonna say Narnia 2 and then give this shell code, and once you hit enter, you pop up the shell. So let's type who am I, and you're still Narnia 2, you're not Narnia 3. Okay, so which means you have to use a shell code that has -p in it. Okay, something like, it preserves effective user ID of Narnia 2. Okay, not the real user ID, which is Narnia 2, but effective user ID of Narnia 2 is Narnia 3. Okay, so let's exit out of here. Let's build our new payload. Let's go to the browser, and we know that 606 has this bash -p. Okay, so which means it will take care of all the privileges and give effective user ID. Okay, not the real user ID. So we'll just copy this and paste it, and let's say shift tab, shift tab, shift tab. Okay, so let's remove this and remove this and remove this, and now we have shell code. Okay, so this is 33 bytes. Okay, let's open up calculator. So 132 minus 33 bytes. Okay, so it's 99. So we need 99 bytes of NOPSLED. Okay, let's say string counter. So we need so many hex 90. So this is 5, and then we got 10, and then we need to say 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so we need to remove this last one so that it is 99. Okay, so now we have 99 no operation characters, followed by this and followed by the return address. Okay, so what is the return address? So we know that the return address is this one. So let's copy this and paste it over here. So now the payload is ready. So we need to give this payload to this. Okay, so we're gonna say Narnia 2 and backtick echo -e, and then give this followed by backtick. Okay, so let's see what happens. So now we got a different type of shell. Okay, so hopefully this is not Narnia 2, this is Narnia 3 shell, because as the shell code says, it needs to preserve effective user ID. So who am I? Narnia 3. Let's get etc/Narnia_pass Narnia 3. Okay, so this is how you get your shell. Okay, so clear. I'll tell you where they'll make mistakes. So let's run GDB Narnia 2. So disassemble main and keep some pointer, let's say break at main plus 81. Okay, so this is all common practice, we already done this. So let's give a payload of 136 characters ending with 42, 42, 42, 42. Okay, so let's see what happens once we do this. Okay, so we have hit a breakpoint over here, so let's continue. Okay, so we have successfully replaced return address to 42424242 words of memory in stack pointer. Okay, so here you can see that it is 42424242 and 414141 and so on. So let's give some more memory. So let's say it is 30. Okay, so now we have some more memory, so let's give 50. So here you can see that it's 248. Okay, so you will think that this is the exact code that actually starts allocating data, right? But this is not the case. If you try to give this data as a return address, then you're actually mistaken. Okay, so if you type 150 or let's say 250 from stack pointer, so let's see what happens. Okay, so this is where we're starting, this is where we keep going, and as you can see, we can see 41414141 from here. Okay, so this address is different, right? So D510, D550 and so on. So if you remember, this is the exact address that we have given. Okay, so D554. So don't confuse with the addresses. Okay, so make sure you try both of them and give ample amount of memory from the stack pointer so that you can identify this data. Okay, so exact memory address of this. Okay, so once you give this address, you're actually able to execute the shell. So we have to begin with Narnia 3. Narnia 3's password is this one. We got it from previous level. So let's clear that. We know that all the data exists at cd/Narnia. So this time our focus will be on these two files. Let's see what this file does. Narnia 3. So this is the usage. So Narnia 3 and some file should be given, and this contents of the files will be sent to some other file. Okay, in this case the file seems to be a null file. Okay, /dev/null. So let's try to give a file to it and let's see what happens. Let's try to give the password of this Narnia 4. Okay, /etc/Narnia_pass Narnia 4. Okay, so let's see what happens. So it's saying the contents of Narnia 4 to a safer place. Okay, so the safer place is /dev/null. So this is not what we want. So we cannot retrieve anything that goes into /dev/null. So let's see the contents of Narnia 3.c file. We have some headers here and int main. So this is the main function and it's accepting some arguments. Some variables are initialized. So IFT, OFT, I'm not sure what this is, but this seems to be the output file. It's sending to /dev/null and looks like that is what happened, right? So we gave this as an input file and this was the output file. So this input file is taken as Narnia 4 file and this output file is sent to /dev/null. So this is not we wanted. Okay, so since this is initialized first and then this is initialized, if we try to give anything into this variable, if we exceed 32 bytes, it will try to overwrite this file next. Okay, so if you remember, all the initialization happens from higher memory to lower memory. So if something exceeds in the lower memory, it will override the contents of the variables or functions which are in higher memory. Okay, so we have seen that in Narnia 0. Okay, so I'm just recapping this. So in that Narnia 0, this was initialized first and then this was initialized. Okay, so it will keep track from higher memory to lower memory. So if anything goes in variable that exists in lower memory, if it exceeds the limit set by the program, it will try to overwrite previously initialized value. Okay, so this is the same case. This has 20 bytes and once it exceeds, it is trying to overwrite the previous initialized variable. Okay, so same thing happens here. If it doesn't contain any argument, print this. Okay, so it is 2 because as you can see, this is program and this is an argument, right? So it is taken as first argument and this is taken as second argument. Okay, this is how in general C program actually sees. Okay, if it doesn't detect any arguments, so it simply says that usage Narnia 3 file and something something. Okay, so same thing happens here and then it exits right there. Okay, so if we give some argument, then this condition will be skipped and then this function will execute. So in this function it says that whatever is the argument given, that argument will be stored in input file. Okay, so Narnia 4 was stored in this I file. Okay, so that is what it's saying. So once this is done, So this condition says there is an output file, and this output file should have read write permissions. Okay, if this doesn't exist and it cannot open the file, then it's going to say error opening the file. Okay, and then it exits over here. And similarly, an input file is checked, this file. Okay, so this file is checked, and this file should have read only permissions. Okay, and once it is able to open this file, this is stored in this input file. Okay, and if it cannot open this file as read only, then it's going to simply say error opening the file. Okay, so copy from file 1 to file 2. So this is going to read this input file, this is going to write this output file, and whatever the contents of this input file are being transferred to output file. Okay, and then once this is done, this will close the files. Okay, so what you have to do is you have to create an input file or use the existing Narnia 4 file in some other way. Okay, so we'll see how we can do that. And this file should have more than 32 characters, and once this 32 characters are filled, this output file will be overwritten, and this output file should also be accessible. Okay, so this file should be so big so that it can overwrite this and also create a new file over here. Okay, and this file should also be accessible, or else we don't know where we can find the contents of the output file. Okay, so the contents of the output file should also be accessible to us. Okay, so we have to create in such a scenario. So let's see how we can do that. So there is a place where we can actually create lots of files, right? So that directory is called temp directory. So everybody knows this. So we just moved to temp directory. So we have to create an input file. So let's say that input file exists in some other directory. Okay, /tmp/ some directory which is more than 32 characters. Okay, so let's type 32 characters including this /tmp and /. Okay, so already 5 characters are done, so you have to say 27 more characters, so that 27 plus 5 will be 32. Okay, so let's say 1 2 3 4 28. Okay, so let's say 27 characters. Okay, plus 28 29 30 31 32. Okay, so till here we can say input file is buffer is filled. Okay, this part is filled. So once this is filled, whatever we type will be going into output file, right? So output file should also be accessible to us, and it should contain less than 16 characters. Okay, so since we can access temp directory, so let's create a subtemp directory over here. Okay, so since this directory doesn't exist, we have to say that mkdir/p. Okay, so this /p will create some kind of parent directory to this, so that this directory can be created. So this directory is created. Okay, so we have to create a new file into this directory, so that when we try to access that file, Narnia 4 file will be accessed. Okay, so we have to create a soft link for that. So let's create a soft link, Ctrl+Shift+V, and then some name of the file. So this file, let's say HMCyber, this file doesn't exist in this directory, so we are creating a soft link. Okay, so to create a soft link, first you need to mention the actual file. So Narnia_pass Narnia 4, and then the soft link that you're creating. Okay, so this HMCyber file will be created in this directory. Okay, so let's say -l. So this is a soft link right now. Okay, so this link is actually directed to this file. So let's also see the permissions of this directory. Okay, so it says Narnia 3 can read, Narnia 3 can write, others can read. Okay, so which means others can access this file, which means if Narnia 4 is there, Narnia 4 can access this file. It can read whatever the contents. Okay, so hopefully this will execute. If this doesn't execute, we have to give 777 permissions to this directory as well. Okay, so let's try without changing the permissions. Okay, So once this is done, we need to also create some file in temp direct, so that that would be the output file that this file can detect. So let's create that file /tmp/hmcyber. Okay, so we have created this file. Let's give this permissions to it, chmod 777 /tmp/hmcyber. Okay, so we have given full permissions to it, so that this file can write into this file. Okay, let's try to run the file. Okay, so the file is in /Narnia /Narnia 3. So this is the file. So we'll give an argument in this format. Okay, and hmcyber. So we're trying to access this file. Okay, so when we're trying to access this file will be triggered, and then the contents of this file will be transferred into output file, right? So since this is the input file, this already has 32 characters, and whatever is excess will be given as an output file. Okay, /temp/cyber hmcyber will be the output file right now. Okay, and this whole thing will be the input file. So let's see what happens. Okay, so copied contents from this file, which is actually this file, to a safer place, which is /temp/hmcyber. Okay, so let's copy this, let's cat this, and here we got the solution. Okay, now we have to log into Narnia 4. So this is the password, clear. So now our point of interest is these two files. Okay, since we are in Narnia 4, we have to care about Narnia 4.c and Narnia 4. Okay, so let's see what Narnia 4 has for us. Okay, it's returning nothing. Okay, so we don't know what we can give, right? So let's see the file Narnia 4.c. Okay, so we have some headers, and we have this statement, and then there's a main function. Okay, and in that main function it accepts some argument, and then a variable I initialized as integer, and some buffer variable with 256 bytes of data is initialized as character. Okay, cool. And then there's a for loop. It says for I equals to 0, environ of I not equals to null, then I plus plus. So we'll see what this environ is. Okay, so if this is the condition, then memset, which means they're setting inside the memory of this environment variable to null character. Okay, which they're saying essentially to make it as a 0 or null. And how long this null character should exist? As long as the string length of this environment variable. Okay, so the whole value of each environment variable is set to null. Okay, so the last environment variable is already set to null. So once this reaches to the end of this list of environment variables, then it detects that it is null, so then it stops executing, and then it goes to the next statement. Okay, in the next statement it's going to check if there are any arguments that exist, and the value of argument will be stored inside this buffer. Okay, so previously we have given this argument, right? So this argument will be stored inside this buffer variable. So that is what this string copy does. Okay, this is where the vulnerability is. They are not restricting any limitation on how much buffer variable should contain. Okay, so it doesn't matter how big this is, it can still accommodate into this buffer. Okay, but this buffer variable can only store 256 characters. Whatever is excess will go into next point of the stack. Okay, which is I in this case. And then even if this one fills out, it has to go to some other area where it can return some return address. So we need to find that address and point that return address to a shell code. Then we can execute that shell code and we can get a shell. Okay, so let's see what this environ is, and then we'll go to GDB. Okay, so we have a manual page for environ, and we'll see what it is. The name is environ, it is user environment. This is how it should be implemented, and this is the description. So the variable environ points to an array of pointers to strings called environment. basically this environ will point to all the environment variables. Okay, so the last pointer in this array has the value of null. Okay, just as we discussed, the last pointer has to be null, and then the for loop exits from there, and then next statement will continue. Okay, so let's get back to the code. So you need to understand that if we can change all the environment variables to null, then we cannot execute anything regarding environment variables, right? But that's not the case with this. So they have deliberately made this for loop because previously in Narnia 1 we have changed the environment variable and we pointed it to a shell code, right? This time we cannot do that, so we have to do something else here. And also this environmental variable is set to null only to this particular shell, okay, only to Narnia 4. So after some time, some cron job should be running so that all the environment variables should be set to its previous states. Okay, so everything's good. So now let's open GDB and try to overflow this buffer and let's see what happens. So GDB Narnia 4 and yes. So the first thing we usually did was disassembling the main, but this time let's try to do without disassembling main to see what happens. Okay, we know that there's Python 3 that exists, so we'll use that to write a Python script and print lot of strings. Okay, since it is 256, let's give under 256 and then see what happens. Okay, so let's hit enter. Okay, so it exited normally. Okay, there's no buffer overflow that happened. So let's increase this value to 260. Okay, so let's see what happened. Okay, it still exited normally. Okay, so let's make it 270. Okay, so now we have some segmentation fault. Where is this segmentation fault is even pointing to? It's pointing to this A again. So this is the return address. This is usually called EIP. In assembly language, EIP is called as extended instruction pointer. Okay, so basically it just points to a different address that's called return address. Okay, so we have to see if we can override this return address and point to something else. Okay, so let's see that since we can overflow this, so let's try to change this value a little bit to understand where it actually exits. In addition to this, let's give some 4 A's, B, and let's change this value to 60 again. So yes, we still got a segmentation fault, but it did not show any return address. So EIP is not been overwritten. Okay, so we'll just increase some payload. So we'll say 262. So let's see what happens. We have a return address and we can see that 4242 exist over here. We'll just have to give 2 more B's, or we'll just have to give 2 more A's so that this B's will be filled. Okay, so let's do that. So it's 264 now. So start from the beginning, and as you can see, all the 4 B's fit exactly to the EIP pointer. Okay, basically return address. So we can overwrite this return address with this number of bytes of data. We'll just inspect the memory stack and see where this actually happens. Okay, so since this is 250 or 260, so we'll just give 260 words of memory. Okay, so x 260 and words x from stack pointer. Okay, so this is examine and this is the number of words of memory to examine, and then this is to show it in hexadecimal format. Okay, and this is the ESP pointer. Okay, stack pointer. So we'll see what happens. So next. Okay, as you can see, this is where it starts and this is where it seems to be ending, and rest of the environment variables, as you can see, it is set to 0, right? So we'll just replace all of this with nops, which basically is no operation, and then at the end of this payload we have to give shell code so that the shell code will execute. Okay, and at the end we also have to give the return address somewhere in the middle here so that it will just slide down and execute the shell code. So let's do that. And you need to also remember that we cannot directly keep hexadecimal code, something like this, using Python. Okay, so let me show you what I mean. So let's hit enter and start from the beginning, and then you go to the stack pointer, and as you can see, we don't see just 90. Okay, we also see C2, okay, which is something else. So instead of using this Python, we have to use something like echo or printf. Okay, so when we use something like printf or echo, we have to give all of the payload instead of giving it as a multiplication of payload. Okay, we have been using this shell code, and this shell code is actually /bin/sh. Okay, and it's only 23 bytes. So let's use this shell code and see if it actually works. Okay, if it doesn't work, we have to go with some other one. So since this challenge actually requires effective user ID to be executed, I'm thinking this will not work. Okay, but let's try it anyway. So this is a shell code. Just remove this, and here we got our shell code. Okay, and since this is 23 bytes, so we have to subtract that from 264 because we already have 264 bytes of data. 23, that would give you 241. Okay, so multiply this 241 with 4 and you get 964. Okay, so this character count should be like 964. Let's see. Okay, it's too much, so let's remove some of it. So we got our 964 payload. Okay, so let's copy this and paste it right before this. This is our payload right now. Okay, and at the end of the payload you need to give some return address. Okay, so let's go back. This is the output that we got previously. Okay, so somewhere in the middle, if you just keep the return address somewhere around here, then it will just slide down and it will execute the shell code. Okay, so let's take this address and write it at the end of the shell code. Okay, we have to write it in little endian format. So \x c0 \x d4 \x ff \x ff. Okay, so this is our final payload. Let's just input something like printf or echo e. So let's say echo e, and then this will execute, and we have to run it as a shell script. So we have to say that this is a shell script by keeping a backtick at the end. Okay, so let's copy this, let's run it and paste it, and let's run it and run from the beginning, and let's continue. Look what we got here. We got a shell, right? So, and just like we imagined, this return address went somewhere in the middle and then just slide down because it is no operation, it will not do anything over here, and then it came to the shell code and the shell code executed. Okay, so let's do the same thing outside GDB. Let's say Narnia 4 and then this, and then hit enter, and we got a segmentation fault. So we have checked that, so this particular shell code is working inside GDB but not outside GDB. Okay, so let's go with some other shell code which also have this effective user ID being preserved. Okay, that is 606. So let's use this shell code and create a payload. Okay, we have created this payload, and this payload has these many characters plus the shell code. Okay, and then a return address. Okay, so this return address we can get it from the GDB. Okay, so it's around D5. Okay, D5, let's say some other thing like 50 or something. Okay, so we've already seen that in GDB. So let's get this shell code and let's try this in GDB, and then we'll try it outside GDB. Okay, so Narnia 4, and then yes, and then run the shell code, and then yes, and we got a shell. Okay, so let's exit out of here and use the same shell code outside GDB. Okay, so exit Narnia 4 and then the shell code. If you hit enter, and we got a shell. Okay, so if you type who am I, you get Narnia 5. Okay, so let's get the password etc slash Narnia underscore pass Narnia 5. Okay, so make sure that if one shell doesn't work, try with some other shell. Okay, as I said previously, either you need to take care of this shell code or you need to take care of this return address. Okay, so rest of the things won't be changing that much. Okay, so now we have to log into Narnia 5 and this is the password. Paste it and hit enter. Okay, we know where the data is, and if you type ls-l, and these are the two files that we need to worry about right now. So let's try to execute without any arguments Narnia 5, and it gives a segmentation fault. Okay, so let's try to run it with some argument. Okay, it now gives some data. Okay, change ice value from 1 to 500, and it also says no way, let me give you a hint, and then this is the buffer, and the buffer seems to be accepting this and storing it inside it, and this seems to be the size of this buffer, and there is a variable and looks like its value is 1. So let's change the payload and see what happens. Okay, so now we have changed the payload a little bit, and now the buffer has increased, and now its length is 8, and this doesn't change at all. Okay, so let's see what we have in the code. Okay, so let's see cat this, and this is the code. Okay, so we have some headers, that's fine, and this is the main function. This function accepts some argument, and I has been initialized to 1, and next we have a buffer variable which can accommodate 64 bytes of data. Okay, and then we have snprintf, and this snprintf has this buffer variable and the size of this buffer and also the value of argument that we are giving. Okay, so this argument has to store inside this buffer, and this line seems to be that the last character has to be 0, which means it can accommodate only 63 bytes of data. Okay, not 64. So printf, and this is what we have seen. Change the ice value from 1 to 500, and once the ice value is 500, then it just prints out good, and then it gives us the shell. Okay, and it also takes care of the user ID permissions and everything. If ice value is not 500, then we're going to get all these values here. Okay, and you also need to see this printf statement which says that I equals to %d, which means it is taking the value of I and printing it here. Okay, so initially the value of I is 1, and next thing it is printing inside the brackets, it's printing a pointer. And whose pointer is this? It's the pointer of I. Okay, so which means the value that we have got here is the memory location for the variable I. Okay, so we can use this to change the value of I. Okay, so once we have understood the code, let's see what snprintf can do. Okay, so if you Google for snprintf, it's gonna give one of the links as this program is. So in this one, they have explained what snprintf can do. Okay, so this function writes string pointed to a format to buffer. So whatever is the format that we specify, that is going to be inside this buffer. Okay, and it also says that maximum number of characters that can be written is buff size minus 1. So we know the buff size, which is 64. 64 minus 1 is 63. So after the characters are written, a terminating null character is added at the end. If buff size is equals to 0, nothing is written, and buffer may be a null pointer. Okay, so they have mentioned this buff size is equals to 0, right? So this is where that statement is. Okay, cool. So this is the buffer, this is where this buffer is, and inside this code, this is that buffer. Okay, and the next thing is a buff size. So we have already seen that this is a buff size and the format that they have mentioned here. Okay, if you see this general statement, the third parameter has to be some format. Okay, so we can keep any kind of format right here. Okay, so this is where the vulnerability is. The vulnerability is in the format specifier. Okay, and this type of vulnerability is called format string vulnerability. So usually we specify a format by specifying this %sign and then some flags if necessary. If no sign is mentioned, then it just takes space. Let's say we keep something like percent and then some character like, let's say X, okay? So if we did not mention anything like plus or minus or something like that, so it's gonna simply take space as a character, okay? So that's what this means. And then we have width, which is optional, and length, which is optional. We can specify the length. Let's say this space character, we can say that it has 20 bytes of spaces, okay? That would be helpful. We have different types of specifiers, and if we say percent, it means print, C for single character, S for string, I for integer, and then O for octal representation, X for hexadecimal representation. Okay, so when we give something like this, it is going to say that we are going to give hexadecimal representation of 20 spaces. Okay, so that would be helpful. We also need to have this n. Okay, so this n actually returns the number of characters written so far by this call to the function. So that's what this means. So this is the general format. So we'll use this to create a buffer overflow that would change the value of this I. Okay, let's see how we can do that. So let's keep some random hex value and see what happens. Okay, so we have already executed something like this, but this time, so let's keep a subshell, and inside this subshell, so let's create some hex characters. Okay, so this hex characters has to be pre-processed, right? So either you can use echo-e or you can use printf. Okay, so let's use echo-e. So let's give some hex characters, percentage hex41. We know that this is capital A, and then let's give 3 more of this. Okay, so let's see what happened. Okay, so there's a syntax error, which means, okay, so this has to be dollar because this is a subshell, right? So we're creating a subshell over here. So let's see what happens. Okay, so we were able to successfully enter this into the buffer. So this will be pre-processed as a, and then it is stored inside this buffer. Okay, but nothing has changed with the value of I. Okay, what if we give the memory address instead of just random A's or something like that? Okay, so we know that the memory address of I is this one. Okay, so let's change this into the memory address of I. So we'll give it in little endian format. Okay, FFFF and then D3 and then 70. Okay, so this is the little endian format of this memory. Okay, this will be pre-processed and this will be stored inside this buffer. We can see that this is stored inside this buffer. So we also know that if you mention the format specifier as %n, we can return the number of characters written so far by this call to the function. So let's see what happens if we do this %n at the end. So this is same and this one is same, but look at here, the value of I has changed, which means this %n has counted the number of characters, which means 4, and this number has to be stored inside this buffer, right? So what does this buffer contain? This buffer contains the memory address of I. So the value of I is changed right here. So far so good. So what if we give some spaces? So let's give some spaces, something like %20x. Okay, so if we did not give any plus or minus, this %20x will give 20 space characters. Okay, so we know that from here. Okay, since this one already has 4 characters and this one has 20 characters, this should return 24 characters, right? So this has to be changed to 24. So let's see what happens. So we got a segmentation fault. So why does this segmentation fault happens? Because it doesn't know where to store this number. Should it store in the first part of the argument or somewhere in the 20 spaces in the argument? Okay, so it doesn't know where to store this number. So we can specify that it has to store in the first part of the argument something like this. Okay, $1. So this $1 will tell the printf to use first argument in the list. This argument is the address of I. Let's see what happens. So nothing has changed here, but this has been changed. So why is that? Because this dollar is detected as a subshell. Okay, so we have to escape this dollar by using backslash, something like this. Okay, so now this thing will be detected as $1, which means first argument. Okay, and then the number will be stored inside this first argument, which will be the value of I. Okay, so let's see what happens. Now this value is same as previous, but this value has changed to 24. So what we want is not 24 but 500. Okay, so let's make it 500 by changing this value to 496. Okay, so 496 plus 4 characters here will give it 500. Okay, so let's see what happens. So as you can see, it detected that we got 500, so it said good, and it also gave us our shell. Okay, so let's say who am I, and we got Narnia 6. Okay, so let's print out the password, and we got our password. Okay, cool. So this time we'll be looking at Narnia 6. So we know where the data is. So ls-l. So our point of interest is this one. So let's see what this Narnia 6 actually does. Looks like it's just printing the usage of Narnia 6. Okay, so it's expecting 2 arguments. So let's try to give 2 arguments. So let's say ASDF1 and ASDF2. So it's just trying to reply ASDF1. Interesting. So what about ASDF2? It doesn't care about ASDF2 as of now, but maybe inside the program it cares for second argument as well. So let's look at this file. So this is the standard headers, and we have already seen that this regards to environment variables and some comments. Tired of fixing values, Morla. Unassigned long get sp void. Okay, so it's trying to define function get sp, which has some instruction over here. So this instruction says that move stack pointer to EAX register. Okay, let's check this out. So look at here, this is the case. So if this is the case, movil actually moves variable value to the EAX register. Okay, so it says move the contents of the memory location of var into number register EAX. Okay, so this is what's happening over here as well. So whatever it's there in the memory, this memory location will be transferred to EAX register. So basically we control the stack pointer, right? So whatever we input actually goes into stack pointer. So we control this stack pointer. So if that memory location is transferred to EAX, we can try to execute some instruction using this. Okay, so let's come down. So this is the main function. It accepts some arguments. B1 and B2 can accommodate 8 bytes of data each. Here we have FP. So basically that FP is just file pointer. So whatever is pointed towards that FP will be opened and shown to us. Okay, so this FP pointer is given as location for puts. Okay, so puts is basically something like printf. Okay, so it just prints whatever input is given to this. Okay, so basically this FP will act as puts as of now. So at the end FP is returned back to us. So FP is acting as printf right now. So this function is calling B1. Okay, B1 is basically the first argument, right? So that is what is returned to us previously. Okay, so when we gave ASDF1, this is the B1. So B1 is returned back to us. So that's what this statement does. So this one, it is checking if it has 2 arguments or not. Okay, so argc is not equal to 3, which means the name of the file and then first argument and second argument. Okay, so basically this is argc of 0 and argc of 1 and argc of 2. Okay, so basically 3. If it is not equals to 3, then it is going to print the usage and then it exits over there. Okay, and then they have given a comment, clear environment variables. So it's going to remove all the environment variables. And next statement is clear arguments. Okay, so it's going to remove some arguments. It's not going to remove all the arguments. So it's starting with I equals to 3. Okay, so which means anything more than 2 arguments will be removed from here. Okay, only 2 arguments will be taken into the memory. So that's what this is. And once this is done, argument 1 will be moved to B1, argument 2 will be moved to B2. And you have to also remember that the string copy does not have any restrictions on how much this argument can be and how much this argument can be. Okay, so whatever is given in argument 1 will be stored in B1. Even though it can only store 8 characters, whatever is excess will be moved to the next one. Okay, so whatever is stored in B2 will be stored only for 8 bytes, and whatever is excess will be moved to different location in memory. Okay, so that's what this is. And then it's checking if it is going to get any stack pointer or not, and then it's going to exit right here. If it doesn't, then it's going to set the effective user ID of the program, and it's going to set the user ID. And once it is done, it's going to exit out here. Okay, so this is the main thing. This is where the vulnerability is. So let's see what we can do using GDB. Narnia 6 and enable debugging, and here we are. Okay, so let's say disassemble main. So it's gonna just disassemble all the main. Okay, this time we have a huge number of instructions. So let's go back. So initially it just prints out the instructions of how to use it and exit over here, and it has some main things that needs to be set and memory set. This is where you're actually removing environment variables, and there has to be one more mem set. This is where you're actually removing extra arguments, more than 2 arguments. This is where you're copying B1, and this is where you're copying B2. Okay, it's gonna get effective user ID, and it's gonna set effective user ID right here. Okay, and once everything is done, it's gonna exit. Let's keep a breakpoint right here in this call instruction. Okay, so let's say break star main plus 316. Okay, you don't have to remember this, you have to remember only this part. Okay, and hit enter. So we have created a breakpoint. So let's give normal values like we did before. So this time we know that it can accept 8 bytes in B1 and 8 bytes in B2. Okay, so to differentiate, we will keep 8 A's and 8 B's. So let's run this and let's see what happens. So we have reached the breakpoint. So let's type info registers to see whatever is there in the registers. Okay, so these are the list of registers. Here we have something in EX register. This is the stack pointer. So let's see the data in stack pointer. Examine 10 words of memory from stack pointer. This is 8 bytes of B, and this is 8 bytes of A, and looks like B2 is separated from B1 by a null character. Just after B1 we have this in the memory. Okay, so what is this? This is EAX register. Okay, so can we override this EAX register by overflowing B1? So let's try that. We'll just override this. Okay, so let's keep 4 C characters. So the C characters represent 43, 43, 43, 43. So this 43 has to be replacing this EAX register. Okay, so let's see if it happens. Let's hit yes, and we have reached a breakpoint. So let's check info registers. We can see that EAX registers now have C characters over here. Okay, which means we can give any address in memory to this particular EAX, and it would execute whatever is there in that memory. So using this, let's try to get something that we can execute. Okay, we know that the system function can execute any command that we have given. Okay, so this is the default bash function. Let's try to get its location. So to do that, we will ask for a pointer of system. Okay, so it just gives this location in memory. Okay, so let's copy this and save it right here. If we overwrite this EAX register with this system memory, we can execute any system command. Okay, so let's give this address to EAX register. So let's run. So this time we have to pre-process this address. Okay, so to do that, we'll use echo. So let's say echo -e, and we'll just run a, and just after that, let's give 4 bytes of this memory. We'll say x30, we'll give it in little endian format. So we'll say d4 xdc and backslash x f7. Okay, so we'll close this and we'll give a space and we'll write 8 B's over here. Okay, so 1 2 3 4 5 6 7 8. So these characters doesn't need to be A's or B's. Okay, these can be any random characters. Okay, we'll close this with backtick and let's see what happens. Okay, hit Y and let's continue. Okay, so as you can see, so detaching after V4 from child process this. Okay, which means a child process was created and then it is detached from it. Okay, which means the system has been executing but it did not have anything to execute. Let's try to overflow this B's and see what happens. So let's give C. So this is also random character. So let's see what happens. We hit a breakpoint. Let's continue. So as you can see, it is trying to execute the C that we have given over here, which means after this B2 buffer is filled, whatever is there at the end will be given as a system command. Okay, to verify that, let's remove this C and type ls. So we want to execute ls command. So let's see what happens. Continue. And as you can see, successfully executed ls command. So let's try to remove ls and keep /bin/sh. Okay, so let's try to get a shell. So let's continue. Look what we got. So we got a shell. Okay, so let's copy this and use the same payload outside GDB. Okay, so let's exit and exit. So let's run Narnia 6, paste it and hit enter. Okay, so we got a shell, right? So let's type who am I? I'm Narnia 7. So let's get the password 7. All right, we got our password. Now we have to check Narnia 7. All right, so let's get to cd/Narnia. These are the Narnia 7 files. So let's execute Narnia 7. Okay, so this is the usage. So you have to give some buffer into this. So let's give some buffer and let's see what happens. There seems to be having a good function. There seems to be having a hacked function, and these seems to be their pointers. And there seems to be some ptrf function which points to this location. This is something that we don't know yet. Okay, so we'll try to find out what that is. Let's open this file, cat this. So these are the headers. There is a good function, there is a hacked function, and there is a vuln function which accepts some argument. And if you scroll down, here is the main function. So this main function also accepts an argument, and if there are no arguments, it's gonna print the usage and exit over here. Okay, if some argument is given, then this statement will be skipped and it is gonna exit to vuln function. Okay, so vuln function will start executing from here, and there is a buffer and there is a pointer to a function ptrf which returns an int. The mem set of buffer is initially set to 0, which means initially all of these characters are 0. Once that is done, it's gonna print good function and the pointer to the good function, and hacked function and pointer to the hacked function. Okay, so this good function is going into this ptrf, which means the memory location of ptrf and good function should be same. Okay, so we have already seen that over here. So this one and this one are same. All right, so once that is done, it's going to print before ptrf function. This is the pointer of ptrf and this is the pointer of ptrf. Okay, so that's what this means. So once that is done, it's gonna print, I guess you want to come to hacked function, and then it's gonna sleep for 2 seconds, and then this good function is again sent to ptrf, and there is snprintf which accepts some buffer, and there is a size of buffer, and there is format that it can accept. So as you can see, this argument is the format itself, and if you go to the main function also, it exits with the argument of 1, which means the argument that we are giving is going to vuln function, and this vuln function is going to send this to the format. Okay, so this is where we have control. Okay, so this is where the vulnerability is also. So once everything is done, it's going to return this function. So let's see what this good function does. The good function just prints out this data. Okay, so welcome to good function, but I set the hacked function and then standard output, whatever is there. And what does this hacked function do? So this hacked function says, way to go, and then it flushes out standard output, and then get this effect to user ID, and then set this effect to user ID, and then gives us a shell. Okay, so what we have to do is we have to use this format string to change the pointer of ptrf from good function to hacked function. Once it returns, it's gonna return hacked function, okay, not good function. So that is what we need to do here. So this kind of vulnerability is called format string vulnerability. Since we can access this good function through ptrf, we have to overwrite the memory location of ptrf from good function to hacked function. So let's see how we can do that. So gdb Narnia 7 and yes, continue. We know that the vulnerability is in vuln function, okay, so not in main function. So what we have to do is we have to disassemble vuln. Okay, so let's see what happens. So you already know this. So this memset is going to make all the buffer to 0, and then it's going to print the usage, and then it's going to print some other values, and then it's going to sleep for 2 seconds, and then it's going to say sn printf. So this is where all of the magic happens. So we'll just set a breakpoint just after this, okay, right here. So to do that, we have to say break at vuln plus 151. Okay, so make sure it is vuln, okay, not main. Okay, so that's where people make mistakes. So we are working on vuln function, not main function. So we will run with some random values. So something like a. So examine 20 words of memory from stack pointer. Okay, so we can see that a is located here, okay, at the start of the buffer, and rest everything is set to 0. So let's pick some other memory location because all of them are set to 0. So let's pick this location, which is this location, and try to do some testing here. Okay, so what we will essentially do is we're going to replace this a with this memory location. Okay, so let's see what happens. So to do that, we'll just craft the payload over here, subshell echo -e, and at the memory location this, right? So we have to say \xcc \xd2 \xff \sff. Okay, so we have to write this in little endian format. So once this is done, we have to specify the format. Okay, sn printf needs some format, so we're going to say %x is the format, and then we're also going to say %n. So let's see what happens. Let's run this. Okay, so let's start it from the beginning, and we hit the breakpoint. Okay, so let's go up, let's see the stack, and here we can see that instead of 41414141, this time we have the memory location. Okay, and in this particular memory location we have 0xb. So let's do some test in some other memory location and see what happens. Okay, so instead of cc, we'll try to give dc. Okay, so let's go up, and instead of cc, we'll give dc. Okay, so start from the beginning and let's go up, and here as you can see, this is changed to dc as usual, but in this dc location this 0b exists. So basically, if we give certain memory location and if we try to give some data, so the data is going to be entering into this particular location. Okay, since this ptrf function is pointing to this good function, so let's try to change this ptrf location, which is this, and in this location let's try to give this value. Okay, so this is in hex format, so we have to change it into decimal format and then give it, so that once it gets into memory it will be hex format. Okay, so let's see what happens. If you type in Google hex to decimal, so you can get one of those URLs like this. Okay, so let's copy this and enter hex numbers and convert it. So this is the value that we got. Okay, copy this and let's go back and let's go up. So this is the payload, and this is where we're trying to convert into hex, right? We'll just paste it over here. So if you remember percentage x, so it will actually convert these values into hex. Here if you see, convert integer to hex. Okay, so we are given some integer and this will convert it into hex. Okay, so once it converts, it will send it to this location, okay, which is this location right now. So let's see what happens. So let's go into the memory. This is same as usual. This is that memory location, and in this memory location there is something else, and rest everything is 20 20 20 20. So if you remember what 20 is, so if you just zoom out, this is actually a space character. Okay, so we know that this percentage x, if we did not mention anything or any sign or plus or minus, so it will just give all the space characters. So this is the one. So if you do not give plus or minus, it's gonna say space character. Once that is done, let's see what this is. So to do that, we'll say x location this. Okay, so that location is pointed to hat function. So basically we have overwritten this location into hat function. Okay, but we have to overwrite this location to hat function. Okay, so we can do that pretty easily, right? So we have to say d2 and a8. Okay, so let's do that. Start from the beginning. We hit a breakpoint. We'll just continue and look at this. Where you go, detaching after v4 from child process this, and we got a shell. So let's use the same payload and run it outside GDB. So exit and Narnia 7 this, and let's see what happens. Okay, so we did not get a shell. Why is that? Because the memory location has changed from A8 to D8. Okay, so we need to check what happens inside GDB and outside GDB. Okay, so if we change this A8 to D8, so we should get a shell. Okay, so D8, and look what we got, a shell. So who am I? Narnia 8. So let's get the password. Cat. All right, we got the flag. So this is the last level in this series, and this is amazing. So buckle your seatbelts and get excited. So SSH Narnia 8, paste the password, clear, go to the location, ls-l. Let's try to execute Narnia 8. Okay, so Narnia 8. So it's expecting an argument. So let's give some argument. Okay, it's just replying. So it's just replying back our argument. So let's give some more data and see what happens. After some time, the data is getting converted into something else. So let's give some more data and see what happens. So there's something being changed, but most of the data is kind of same. Okay, so it cannot read the data. So let's check the code. So cat this. Let's start with main function. It is expecting some argument. If there are some arguments, it's gonna execute this func function, or else it's gonna just print the usage. So let's see this func function, and this func function takes the argument that we have given. So let's see that, and this argument is going into this particular location, and this is again storing into this particular pointer, or you can say character array. Okay, so this is another character array which can hold 20 bytes of data. All the size of the block is set to 0. Okay, so all the memory inside this block is contained 0. Okay, so after this there is a for loop in which all the data in the block is sent into this block byte by byte, not all at once but byte by byte. Okay, so once this is done, whatever is in the block is going to be printed out. So that's what happened over here. Okay, it's just printing out, but there's something that's just blocking. Okay, so let's find out using GDB. Okay, so GDB Narnia 8, let's say to open it quietly. So hit Y. So where is the vulnerability? So if you check, there is no restriction of how much block can be sent into BOC. So this is where the vulnerability is. So this B is sent into blah and this B is taken from the argument. So we can control this blah. Okay, we can try to overflow this BOC using this blah. So this is where the vulnerability is. So as you can see, the main function does not have much. Okay, only in the func function we can find some vulnerability. So we have to disassemble this func function. So disassemble func. So as you can see, so this is the mem set where all bytes of BOC is set to 0. Once that is done, everything is sent into BOC, and once that is done, it is going to print BOC. Okay, we'll just keep a breakpoint just after this print function. Okay, somewhere around here. So we can say break at func plus 110. Let's run with random arguments. All right, we hit a breakpoint. So let's examine 20 words of memory from stack pointer. So we can see that our 4 bytes of A has been moved into the memory, but we can accommodate 20 bytes of data into BOC. Okay, let's check what we have in registers. If you type info registers, as you can see, this is the stack pointer which starts from here. So that's what we have expected as well. And this is the base pointer. Okay, so basically base pointer is just like a copy of stack pointer. Okay, so we can just ignore it whenever this comes. Okay, but we have to see in memory where this actually locates. Okay, so it says D33C. Okay, D33C located here. Okay, which means this is the EBP. So we'll just keep that in mind, and remember that this ESP and EPP both are same, but EBP is like a backup of ESP. If we want to change this memory address, we can keep some random characters over here. So what do we see after this EBP? So we have this thing, right? Let's see what this is. Examine word in memory, and this is the location. Okay, as you can see, it says that it is main plus 23. Okay, so we haven't seen what is inside main. Okay, so let's check that. So as you can see, main plus 23 is a return of func function. Okay, so this is kind of a return address of func. So let's make a note of what we have seen so far. Okay, so we have seen a BOC array which contains 20 bytes of data, and we have seen some address. Okay, so we don't know what that is. So that contains 4 bytes of data, and next we have seen that EBP exists, and this one has 4 bytes of data, and next we have return address. So return address of func. So this also contains 4 bytes of data. So what is this one? So let's check that. So this is that address just after BOC. Okay, let's copy this and let's examine what we have here. So looks like we have AAAA inside this as well. So let's see that in some other format. So AAAA. Okay, so this is our input, right? So this input is already inside BOC. So there is only one other variable in which these A's can contain. Okay, so if you check the code, initially our input is going into B and then blah. So this is the memory address of blah. So let's copy this and replace this with star blah. So now we have BOC and we have a memory location of blah, we have EVP and return address of func. So let's check this address inside memory as well. Okay, so how to check that? We have to extend this value. So we'll just say 200 and we'll just go down and see this value. Okay, so that particular value is D588. Okay, so let's go there, D588. So this is where our data is. All right, so there's one more thing we need to check. We have given 4 A's in the beginning, so let's give that one more time. So let's execute and let's say 10 words of memory this time. So this much is enough. Everything is covered over here. Okay, so BOC, blah, EBP and return address. Our point of focus is this one right now. Okay, so we gave 4 A's and this is the memory address. Okay, so let's try to give 5 A's and see what happens. As you can see, the hex value is reduced by 1. So let's give 6 A's and say yes, and then say this, and as you can see, hex value is again decreased by 1. Okay, so what's basically happening is, if you try to increase your input, blah pointer is decreasing its value. So keep this in mind. So we need one more information, that is, where should we point this return function to? Okay, so if we can control this return function, we need to point it to a shell code. So let's create a shell code outside GDB. We are not only creating a shell code, we are exporting it to environment variables. Okay, so let's say shell code. From where do we get the shell code? So we can get the shell code from one of our previous levels, which is 606. Okay, shell storm 606 will give this bash shell, okay, with -p, which would preserve effective user ID permissions. Okay, so let's copy this and our shell code is ready. Initially, let's keep some no operation characters. Okay, so why do we need these no operation characters? If we do not keep these no operation characters, so we cannot precisely keep the exact location of start of this shell code. Okay, so if we find out some location and if we keep the return address somewhere in the middle of this no operation characters, then it will just slide down to the shell code and the shell code would execute. Okay, so that's the main idea of this no operation characters. So let's copy this, let's paste it over here, let's save it. Now we need to know where the shell code is located in memory. Okay, so to do that, let's go to GDB and you can still use any program from Narnia. So basically we don't want to run anything, we just want to start the program and then get the location of the shell code. Okay, so it's very simple to do. So break main, you're not executing anything, you're just setting a breakpoint at main. You don't want any of this program to run. All you have to do is run the program. Once it hits the breakpoint, you have to examine the string of a pointer, which is like a character that is located in environment. Okay, so basically you're calling one of the environment variables. So if you see that we got a shell, but we don't want shell, we want shell code. Okay, so we want this. So to get the next environment variable, all you have to do is keep a +1 at the end of this statement. Okay, so now you get shell code and you got rest of this statement as well. Okay, so this is the actual shell code. Okay, we don't want all these variables and everything, we only want this part. Okay, to get only this part, all you have to do is take this memory and say XS and give this memory plus, let's say, 5. Okay, so you can see that this shell has been disappeared over here. Okay, only code is there, so you have to remove this code as well. So this is 5 more characters, so you have to say remove this 5 and keep 10, and now you got the shell code. So this is located in this 4A location, so you copy this because this is what we need, shell code location in memory. So once you got this location, you don't need this GDB anymore. So let's exit out of here, let's go back and create some payload. So now we know what to do. We need to target this return function and point it to this location. How can we do it? We will just fill this with 20 A's. We'll fill this blah with some memory address by calculating what we can do. Okay, so we'll just keep it as empty as of now, and we can keep anything in this BBP. So let's keep some 4 A's because it has 4 bytes of data and this is 4 bytes of hex data. Okay, so to get the memory location of this, we have to add 20 bytes of BOC and 4 bytes of this, and 4 bytes of this, and 4 bytes of this. Okay, so whenever something is added into this box, this blah pointer is decreasing. Okay, so let's add 20 A's because that's the buffer size of box. So how can we do that? Let's say Narnia. Let's create a subshell. Let's say echo -e and 20 A's. So let's keep that in quotations. Follow this with some program called XXD. So this XXD program will take the output of this Narnia 8 execution and give a hex dump of the memory. Okay, so it directly gives the output from the memory. So we all have this 41414141, and then after this we have this blah pointer, and after this we have EBP, and then the return address of func. So we are not inside GDB, so these values are accurate. Okay, since we are filling this with 4 A's, so we don't want that, and we are just overwriting this value with this value, so we don't want that as well. So all we care about is this blah pointer. Okay, so let's write that 0x ff d538. so we got this address after we have given 20 A's. Okay, we have to calculate what happens to this memory address when we give 4 plus 4 plus 4 12 bytes of data. We have to give 12 bytes of data. So when we give 12 bytes of data, 12 hex values of blah decreases. So with this logic, what we can do is, let's take last two values of hex, which we can represent it as 0x38, and 12 bytes, that is in decimal, so 12 decimal. Okay, so we have to convert this 12 decimal into hex. Okay, so let's say decimal and remove this and say 12. Okay, so as you can see, it has converted it into hex, and the hex value is C. Okay, so basically you want to remove 0xc from 0x38. So let's remove that, and what would be the answer? So let's go back, let's go to hexadecimal, let's remove this and say 38 minus C. Okay, so now you got 2C. So let's copy that and keep it over here. So this would be given inside this memory. So let's remove this and keep this. Okay, so this would be our new memory address after we have kept all of these values. So let's build the payload. So the payload will be like 20 A's. So let's fill 20 A's, followed by this in little endian format, which is \x2c \x d5 \x ff \xff. Okay, and then followed by 4 A's and followed by this memory address. So \x4a \x d5 \xff \sff. Okay, so this is our new payload. Okay, let's go back. We don't need this xxd anymore, so let's remove this and paste this. So let's see what happens. So we got a message called illegal instruction. So what is an illegal instruction? So before we understand what is an illegal instruction, let's see our payload. So we have filled this buffer, which is buffer of box, so we don't care about this. So this we calculated, so we don't want to worry about this as well. So this is EBP, so we don't care about this as well. So all that we need to care about is this return address. Okay, so this return address we got it from GDB. Okay, so we have to slightly adjust over here to get correct return address. Okay, so this illegal instruction is basically saying that you are giving a location in memory and I cannot understand what to do with the data inside that memory. Okay, so that's basically illegal instruction. Okay, so let's keep changing this value slightly so that we get what we want. Okay, so we want to slightly move this forward. Okay, so why we want to slightly move this forward? So we want it to place somewhere in between this knob sled. So once it reaches one of these knob characters, so it will just keep sliding down until it reaches the shell code. We have changed this to 4A to 4F. So now we are getting segmentation fault, which means previously we are sending it to a location where it cannot understand what to do, but this time it tries to process it, but it cannot process it. So let's keep moving it forward. So let's keep 5F and see what happens. Okay, so we got a shell. So looks like this location has placed itself into one of these knob sled. Okay, let's see, who am I? I'm Narnia 9. So let's get the password, cat/etc/Narnia underscore pass Narnia 9. So finally we have completed Narnia 8. So let's try to get into Narnia 9 and see what happens. And exit. So let's go to Narnia 9, paste the password. So as you can see, we don't have a Narnia 9 file. Okay, so if you type ls in home directory, we have a congratulations message. So you are a lead, next please. So hopefully you understand how to solve this Narnia 8, and I'll see you guys in the next one. Peace.